Good afternoon, everybody. That's in Virginia. Good morning to Bill, who's on the West Coast and is our presenter again today. We'll get started momentarily. We're just going to give it another minute or so to let people join and get situated. Okay, I think it's time that we can get started. Hello and welcome to today's SolSmart virtual training. This is session 2 of a 3-part series that we're conducting for Virginia localities. My name is Nick Kaza and I'm a program manager focusing on energy and sustainability with the National League of Cities. Today we will continue discussing the simplified solar permitting process. I think our primary focus today will be on the electrical side of permitting. Before we get started with the presentation, I'd like to review some webinar training details. All attendees are muted and will be throughout the session. This training is being recorded and the recordings will be available online. And please submit any questions to myself or one of the organizers through the question feature in GoToWebinar. If that isn't working correctly, you can send me an email at kaza@nlc.org. If it's a question we can answer live during the training, we'll try and do that. If not, we will follow up with you in an email. Here's a quick look at today's agenda. I'll give a real brief overview again of SolSmart, and then we will hear from Carrie and Elizabeth about the SolSmart initiative that's going on in Virginia in partnership with Virginia's Department of Mines, Minerals, and Energy and the Virginia Solar Initiative with UVA. And then from there, we will, as I said, get into the real fun details with Bill Brooks from Brooks Engineering to focus primarily on the electrical side of permitting today. So with that, I will turn it over to, well, actually not Carrie yet. It's my role still. This training is brought to you by SolSmart, a national designation and technical assistance program for local governments that's funded by the U.S. Department of Energy. The SolSmart program provides assistance to local governments to enhance their solar markets, making it easier and more affordable for homes and businesses to install and access solar energy. Now I will turn it over to Carrie Hearn with DMME and Elizabeth Marshall from UVA.
Thank you, Nick, and hello, everyone. My name is Carrie Hearn, and I'm the Solar Program Manager at DMME based in Richmond, Virginia. And I'm one of the SolSmart technical advisors for Virginia, working with Nick and Elizabeth Marshall from UVA. And we're very pleased to bring no-cost technical assistance to localities across Virginia to help assess opportunities around solar in the local government structure, and hope that this series is one of those opportunities that can help identify improvements to support processes and programs that you are offering for permitting solar in your community. I also work on clean energy implementation, as was laid out through the Governor Northam's Executive Order 43, and that was set forth through the Virginia Clean Economy Act this past legislative session. So with that, I'm happy to turn it over to Elizabeth Marshall.
Good afternoon, everyone. I'm Elizabeth Marshall from the Virginia Solar Initiative. The Virginia Solar Initiative is housed within the Weldon Cooper Center for Public Service at the University of Virginia. And as such, our focus is on developing policy recommendations and guidelines and delivering technical assistance to localities to help them adopt and implement policies and procedures specifically to help further the adoption of solar at all scales, so at the residential, commercial, and even larger utility scales. So we're pleased to partner with DMME and SolSmart to bring this training to you today. We hope it's useful, and thanks to those who are joining us for part 2 and who attended part 1, and welcome to those who are joining us for the first time. Thank you so much. Nick?
All right, thank you very much, Carrie and Elizabeth. Bill, audio check, can you hear me?
Yes, sir.
All right, and I can hear you. I am making you presenter right now.
Okay.
That should be sent.
Show my screen. All right. And now let's see.
Real quick word, everyone. We're really grateful that Bill is here today. As we've kind of alluded to, he does live on the West Coast in California, and so there's a challenging situation going on with the wildfires, and we're just grateful that he is able to be here today.
Great. Well, thanks, Nick. And it's good to be here. I guess it's a good context for our discussion today, but we are in the middle of a pretty massive wildfire that swept through my neighborhood and my community. I got back to my house again. We were evacuated yesterday at 2 o'clock in the morning. And the fire swept through our area. Neighbors lost their houses. We were very, very fortunate. The fire went around our house and the firefighters protected it. So don't want to defund the fire service or the police service anytime soon, because without it, we wouldn't have a house right now. So that being said, there's a lot going on in the solar world, and these wildfires are just one of the things that are pushing folks to want to have solar. Ice storms, hurricanes, you guys are pretty familiar with both of those things in Virginia. And so the realities of the challenge of electrical power is one thing, but it's the other thing is that back in the old days, when I grew up, and which wasn't that long ago, 30, 40 years ago, okay, fine. When the power went out, it was kind of fun. You know, you lit the candles and you hung out, and you might play a board game or something like that. We didn't have TV growing up anyway, so that was weird. But nowadays it's a little different story, and the internet and telecommunications is so dependent on electricity. My house is a pretty good example of that. And as I drove through down transformers and power lines in the middle of the road this morning to get to my house, to get some of my solar projects up and running, it's pretty obvious that I'm not going to have power for a very, very long time. And so, you know, I'm in a special case right now, but I guess I get to live it, and that's part of my I don't know, part of the curse, something like that. But when we left off last time, we were talking about, we talked about member attached systems. That's where we actually screw into the trusses or rafters of the house. And we just started talking about sheathing attached. We're going to talk about that briefly, and then we're going to go through the electrical stuff in this session. And then we'll open it up to some questions. Yeah, if you watch the news, you'll pretty much see what my neighborhood looks like. So if you're wondering about that, you might even see some shots from my neighborhood, because it looks like a war zone. Okay, so with sheathing attached systems, the snow load requirements are the same, 60 pounds per square foot, which the entire state of Virginia, except for maybe one or two, the highest elevations. Even there, I think 60 pounds per square foot is good. So nobody lives there anyway. Wind loads no greater than 140 miles per hour. And I think we saw from our graphs last time that actually Virginia except for maybe the Delmarva Peninsula, has nothing over 140 miles per hour. And then exposure D, waterfront. Well, Virginia has plenty of waterfront. Waterfront that's got 1 to 2 mile access, less of that. We talked about that last time. And then steep hills, those are the same things we saw for member attached systems last time around. And then mean roof height with sheathing attached is a little lower. It's 30 feet, which means that the ridge of the roof is no greater than about 35 feet typically for a mean roof height of 30 feet. Certainly, I've never seen a subdivision with a mean roof height over 30 feet. Maybe some multi-family 2, 3, 4 unit houses could get that tall if they're 3 stories. But even then, even a 3-story house is a tough time pushing 30 feet as a mean roof height. Roof structure meets the International Residential Code, and we're dealing with either manufactured trusses or kiln dry rafters. This gets into the fact that we're counting on the nailing off of the sheathing, and we're attaching to the sheathing, which is then transferring the load from the sheathing to the rafters. We specify the type of rafters that we're talking about. There has been some information, we may talk about a little bit more later, that green wood installations may have some challenges, and in the future the building code is eliminating those options, or at least requiring ring nails or larger size nails, because it's been found that green rafters will recede from the fasteners and reduce the structural capabilities of the sheathing. And then again, no structural damage. And then something called tributary area actually matters. Tributary area, it means the area essentially that's attributed to each anchor on the roof becomes important to us, because we're going to anchor this thing throughout, and where it's how much of the system is being anchored by each anchor, the area that it holds down, it becomes important, because that has to do with the wind loading. Okay, so we said 140 miles per hour, and there you see even Delmarva Peninsula is below 140 miles per hour. There may be a few places there, local areas. We're not going to get into the details of that. Those folks would know that, but it's unlikely that Virginia would have any trouble with this particular issue. And you can see that most of the Southeast, with the exception of the Gulf Coast, the outer banks of North Carolina, South Carolina, and southern Florida, all are less than 140 miles per hour wind regime. Bands of strength become important. Now, this is a concept that was it's learned in other areas, but it became important for this particular aspect. And what we mean by sheathing attached is we're actually putting the anchors right into the roof decking. We don't care where the rafters are. We don't care where the trusses are. We're just going into the sheathing. So there's some very real benefits to doing this. And some people say, well, I just don't believe in that. I think everything should be attached to rafters. And I was one of those folks, and I preached, you got to connect to rafters or trusses every single time. In California, that was all part of my training materials. That became the culture of how things are done, and I had a major part in that culture. But moving forward, hitting rafters is probably the most challenging part of a roof installation. I've done plenty of roof installations myself, and I can tell you that that's the hardest job by far, is making sure that you hit those rafters and you hit them dead center. Very difficult to do. So because of the difficulty of that, there are some professionals out there that do a wonderful job of it. They're excellent at it. They know 5 different ways of doing it, and they employ whichever way works for the installation they're in, and it works, and they're off and running, and they do a beautiful job. And then there's the rest of everybody, including me. The rest of the world is a much, much larger set than that first set of professionals that's super good at it. And so the nice thing about sheathing attached is that it really, the level of skill necessary goes way down, and it gets into my ballpark quite nicely. And so that's what we're looking for, and that's the reason I'm encouraging this type of installation. We're starting to see it more and more. It's probably 20% of installations now are sheathing attached, maybe a little less, but it's growing rapidly. And so anyway, these are the anchor points that we see on the roof, and you notice that they don't line up with the vertical lines. These vertical lines are the trusses. They don't necessarily line up with occasionally you might hit one, like that one in the bottom left corner, that one hits it. But what's really important are these darker rectangles that are wider than they are tall, and those are to depict sheathing. The way that we install sheathing is we start at the edge of the roof, the eave of the roof, and we work our way to the ridge, and the decking runs landscape fashion, if you're familiar with landscape and portrait printing. So the decking, for those of you who may not be familiar, for those of you who are familiar, sorry for this remedial lesson. The decking goes horizontally like this, and then we stagger each row so that the sheathing actually goes in 4-foot steps back and forth, and it makes a very, very strong roof. And it has to attach to all the rafters, of course, and nail off. And what we find is that the center third in the short dimension, so these are 4x8 sheets of decking, typically oriented strand board, it's called OSB, or plywood, the two things that are used for decking. And that in the 4-foot dimension, not the 8-foot dimension, but the 4-foot dimension, the middle 1.5 feet. Okay, so if you took this 4-foot dimension and you split it into threes, actually 3 16-inch sections, the middle 16-inch section has twice the holding power of the edge 16-inch sections. Okay, and that's on average. And we have in our guidelines, we actually have the data that generated this. And what that says is that if we're in the band of strength, which is the middle third of the 4x8 sheet, then we get twice the holding power, and we can count twice the holding power. If we're on the edge, like you see here in the middle of the array, these two rows are in the edge, then we're going to get half that holding power. It's not zero, it's just half. And that's fairly obvious if you think about it. This thing's nailed off. If you wanted to pry one of these sheets of plywood off the roof, you would start at the edge, not in the middle. In the middle would be really hard to do because it's going to resist you from both sides. But if you start at the edge, you can basically cause the edge to give way and rip, peel it open like a can opener, if you will. And so that concept is a real concept, and that concept, it transfers into this. And then we can take that into account, put it into our modeling, and determine as the wind speed goes higher and higher, when we have to be in bands of strength and when we don't. Now, I'm not gonna go any more detailed than that. That's probably more detail than most people ever wanted to hear, but that's what that's all about. And there's a lot of detail about that in the guidance. All right. If the anchors are not in bands of strength, which is what I would recommend for people that aren't familiar with things, then we can set a few guidelines and say the array has to be more than 3 feet from the edge of the roof in all dimensions. That's ridge, sides, and eave. And then also the tributary area of each anchor needs to be 9 square feet or less, which is about roughly half the area of a typical 60-cell module that's used for residential solar applications. And then this would be restricted to wind exposure B. What's wind exposure B? That's going to be your subdivisions and things like that, where you have lots and lots of buildings and trees that are blocking the wind, and so the wind doesn't have any direct access to the house. If you go to wind exposure C, that would be like a house in the middle of a 40-acre field. You've got plenty of room around it, and let's say there's no trees or anything blocking the wind, that would be exposure C. And then exposure D, which we talked about in review again before, is going to be waterfront with more than a mile of access across the waterfront. and those people are rich people, and most of us on this call are not rich people, and we don't care, and so they can hire an engineer, but their wind loadings are dramatically higher. Also, if you're on this 5% grade or higher, which there's plenty of that in Virginia, but those are typically going to be houses that are on the top of a hill somewhere with lots of room around them. So so anyway, that's the restrictions if you didn't care where you put the anchors on the roof at all. And then the next slide gets into if you got all the anchors in bands of strength, then you can go way up. 140 mile per hour for your exposure B, 120 mile per hour for exposure C, and you can go to larger tributary areas and all that kind of stuff. And so again, I'm not going to go into any more detail, but that's the fun stuff. And then the last thing with anchor attachment is making sure that the anchor itself can attach to the sheathing and not pull out of the sheathing. And so it has to have a design strength of at least 166 pounds in order to transfer that weight to the sheathing and not tear it out, tear the anchor out, which means that it would pass an ultimate uplift capacity test of 3 times that, which would be 520 pounds. And then if any structural item in these processes, whether it's sheathing attached or member attached, can't be checked off, then the installer can take it to a professional that can then look at that area that didn't meet the requirement and see if that, along with all the other things, they can determine whether or not there's adequate structural strength or whether they need to augment it at all or do something slightly differently than the guidelines show. Okay, so that's it for structural. Before I dive in any further, are there any questions? I know there's a chat window people could ask questions on. I just want to, before I dive into the electrical, I just wanted to make that available and see if anybody had any quick questions before we dive into electrical. We'll still have options when we get to the end to talk about these things.
Yeah, I've been monitoring the chat, Bill,
okay.
And the questions feature, and I haven't seen anything come in.
Okay. Great. Well, this is a good time to remind folks that if you have questions, we've got quite a few folks on this call, and that's great. I'm glad I was able to accommodate you guys and that our house didn't burn down. But think about questions. Love to answer questions that occur to you. If you've got a question in your mind about this stuff, there's probably 10 other people on the call that have the same exact question. So I appreciate and we'll give you time at the end to do that. All right, so let's jump into the electrical requirements. These requirements I've really boiled down over the years. Started out a little more complex and they've gotten a lot more simple over the years. Largely because the equipment's gotten maybe more straightforward, more packaged, if you will. But our modules, our DC converters, which is a common way of connecting to modules and inverters, these things are all listed products nowadays. We'll probably do a session soon about energy storage systems. I've got 4 different energy storage systems running on my house and learning an awful lot about those systems. And a lot of it is very good news, and some of it is I'm upset, pissed off, and I'm going to be making some phone calls today about how some of these systems operated or didn't when I really needed them most, when my house was in danger. So we'll get those things ironed out. That's why I do what I do, and so that you guys don't have to deal with that. But the products, the listings are becoming, and the packaging is really becoming nice. And on the energy storage side, we're not going to get into details of energy storage. We're going to focus on solar-only projects. But like I said, in the near future, we'll do some energy storage stuff probably in the next month or 2. Array mounting systems, UL 2703 certified for bonding and grounding. So there's a new UL standard. Well, it's not that new. It's probably 4 or 5 years old, where products now are listed to this standard for bonding and grounding, the aluminum frames, the racking materials, all that kind of stuff. And alternatively, they could use grounding devices. to bond things together. Those are the two different ways that we ground and bond stuff, and that's certainly a big concern of local jurisdictions, that things are well grounded and well bonded together. And then the array consists of no more than 2 series strings per inverter input. Some inverters have 4 inverter inputs, and so you could do up to 2 strings per input, however. And then no more than 4 strings total per inverter. And that's the way a lot of systems are being run today. They might have up to 4 strings of modules running into them. Okay, continuing the electrical requirements for Simplified. The field installed array, basically the exposed wiring, so all the cabling that we have that connects the modules together or connects the DC optimizers or DC converters together, is no smaller than 12 gauge PV wire or manufactured cable. Those are the 2 options that are pretty much out there on the market, and so that's going to be a pretty ubiquitous compliance requirement, and easy to comply with because the products are there and they're used universally. All PV source circuit wiring in raceway is no smaller than 12 gauge THWN-2 or XHHW-2 or IHW-2, and those products are also very readily available, but all our calculations are based on these types of wires for ampacity and conduit fill and all the things that you have to worry about on the electrical side. Most of you are probably not electrical people, but the people that are electrical really care about those things, and they should. We're really not going to have any combiner boxes, so C really doesn't come into play very much. And then D, PV system circuits meet the requirements for controlled conductors that are part of rapid shutdown. So we're going to make sure that the system is a compliant rapid shutdown system, which again is a very common compliance requirement, and the installers and the products are readily available out there. Okay. Total inverter capacity is no more than 15.3 kilowatts, which is a very large system, but it's still, when we look at the requirements of 705.12 and the requirements of how we interconnect things, it makes it easier if we limit the total amount of power. And there's other reasons why the total amount of power might be limited in a place like Virginia. Dominion Energy and the other Virginia utilities will probably have limits on the largest systems that you could interconnect through a simple interconnection agreement. And so those are also relevant, and we're not trying to go into all the details of every single utility's interconnection requirements. We're just saying from an electrical code point of view, if we limit it to no more than 15 kilowatts, it'll make our installations easier. And most of the installations are going to be between, I'd say, 5 to 7.5 kilowatts. 7.5 kilowatts is a magic number for a 200 amp service, and we're going to see lots and lots of those types of systems. You might hear my daughter in the background. I apologize. I guess we don't have to apologize anymore. We're in COVID world. Nobody cares. But I have a special needs daughter, and she is with me here as we are evacuated at the moment at my son's house. Load side connection complying with 705.12b, and supply side connection complying with 705.12a, and that's just the parts of the code that are relevant there. Equipment's rated for the maximum DC voltage applied to the equipment. So we got to, really the only thing we have to worry about on the electrical side is making sure that the ratings, which are temperature dependent and they are location dependent, that's the real location dependent issue, meet the requirements. And we have guidance. Here's a website that tells us what the ASHRAE extreme annual mean minimum dry bulb temperature is for your area, and you can look that up. And in fact, let's just do that for a moment. We've got the time. I'm gonna just pull that up for you very quickly, and we're gonna just go to Solar ABCS, permitting. Oh, it looks like this computer's been there before. And this permitting site I put together over 10 years ago, 11 or 12 years ago, and it's still valid even though we've updated the process. The process we're using today is the updated one. There's this older process that's there. And let's just go to Charlottesville, Virginia. Charlottesville has been in the news quite a bit in the last couple of years, and so you guys are famous. And where's your airport? Okay, hold on. Let me just see if I can control scroll out. Yeah, we don't even have a place. All right, we're gonna go to Lynchburg. Lynchburg Regional Airport. The extreme minimum is -15 degrees C. And let's say go to a colder place. Let's say up here, Staunton, Shenandoah, -17, a little colder there. As you go up here, it's about the same, -15, -14, -17, -16. So you see the state of Virginia is pretty close. Now Roanoke's a little bit higher, but look at that. Not so much. Blacksburg, Hillsville. I got a friend of mine from Hillsville, all -15s. Marion. Okay, so we're going to say that the state of Virginia is somewhere between Virginia Beach, which is -8, to about -17. That's your range. And if you were to look at the code and what the temperature multipliers are in the code for that, I'll just bring up the code here for a second. Hopefully you'll be able to see this. I'll blow it up big enough so you can. We're just gonna go to the table in the code that deals with temperatures so that you can witness how lovely the electrical code is. If you've never seen the electrical code, here it is. By the way, the background in the electrical code you see here, it may be difficult for you to see in this webinar. That's a PV array on the 2017, on the cover of the 2017 National Electrical Code. And ladies and gentlemen, I had something to do with that. That's in my career, I consider that probably the highest point of my career, is that photovoltaic systems have become such a prominent part of the electrical code when we were a weird stepchild not long ago that we made the front cover. Okay, so we said -8, which would be a multiplying factor of 1.14 on this table, to -17, which is 1.18. So that's the range of multipliers if you were to use a multiplier. Now, there are other options. We can actually use coefficients and things like that. But in these simplified guidelines, we're using this table, which is 690.7, the table for crystalline silicon. And this is a very simple table, and these are the multipliers where you increase the rated voltage by this amount, between 14 and 18%, and that gives you your actual temperature. So this is that table 690.7 value. We stick that in there, and let me get back to this slide. And that's just to explain, we might have a rated voltage of, let's say, 45 volts, and then we take that 1.18 or to whatever it was for your area, and then you come up with the voltage, and then you determine whether or not that is within the ratings of the equipment. Okay, we could have a DC to DC converter that has a maximum voltage rating. That voltage rating could be 60, 70, 80 volts, something like that. And then we could have the maximum number of DC converters that are allowed in series. And so if we're using DC converters, then we put that in. If not, obviously, we either just don't fill it in or put NA. And then the maximum voltage with the maximum number in circuit, that's usually controlled by the inverter. It might be 380 volts or something like that. If we're running modules directly into inverters, then we will be putting them in series, and so we run through this voltage calculation here, and this allows for multiple inverter inputs and multiple inverters, and we'd fill in, depending on how many input inverter inputs we have and how many inverters we have and all that. Now, when I say we, I mean the installer, the contractor is going to fill this out. The local jurisdictions just seeing that the equipment is, the ratings are filled in and they're within the ratings of the equipment. And then we have standard electrical diagrams, and those standard electrical diagrams describe the system, and to the extent that simple systems can be described by these simple diagrams, we'll use them, and if not, then they're going to have to provide a diagram in order to do that. And then the question comes, well, if you can't fit into one of these simplified permitting diagrams, we're not going to guarantee, as a jurisdiction, we're not going to guarantee that we can provide you a simplified permitting process, because the whole idea behind this is to constrain all the options. There's 1,000 different options out there, and part of having this box of simplified permit information is that we're constraining the options to make it easier for enforcement to review the permits, but also provide an incentive to the installer and the owner to say, hey, if you want to go through the simplified process, get in the box. All right, forget about all these other little cutesy things you could do. Get in the box if you want a simplified permit. If you want to do battery storage and you want to have backup systems and generators and all that other stuff, that's beautiful, that's wonderful. In fact, right now, where I live, that's preferred, but you're not going to do that in a simplified permit just yet. Now, we'll get there maybe someday, but right now, not going to happen. So you're going to go through a more standard permitting process, which could be more lengthy because it's going to be significantly more complicated. And so let's talk about a few examples, and then we'll open it up for questions in about 10-12 minutes. Okay, so let's talk about the standard plans for central, or what we call string inverters. We're going to say no more than 15 kilowatts. We said that we're going to talk about residential services, which are called typically 120, 240 split phase AC services, rated no greater than 400 amps. Now, 400 amps is a very large residential service. 200 amps would be a typical residential service, and then 100 amps would be considered a smaller or older residential service. So a lot of services that were built before 1970 were 100 amps. Many people have upgraded to 200 amps over the years because of air conditioning systems. And then since the 70s in Virginia, because of the large use of air conditioning in all places except for maybe the western cooler parts of the state, we have air conditioning, and most houses have 200 amp services. And then it's not intended for more than 2 inverters in these examples. So let's just take an example of a 7.6 kilowatt, that's a magic number, central inverter system. And we have some fictitious products here just to show you. We've got some 360 watt modules. We got 27 360 watt modules made by American Solar, which manufactures in Malaysia, let's say. Because nobody makes anything here anymore. 7.6 kilowatt American inverter manufactured in Taiwan, 7,600 watt system. And then we have an OmniRack Mod 5.0. That, my friends, would be extruded aluminum and would be manufactured in the United States of America with aluminum processed from, I don't know, Siberia. Sheathing attached. Okay, so in this case, we're going to go jump you right into sheathing attached, like we talked about already today. And then we're going to say that the house has got a 412 pitch, very common for Virginia. Low pitched roofs are common. House built in 1988, got a comp shingle roof. That probably describes several 100,000 houses in Virginia, and quite a bit of that construction. So let's talk about the compliance document, the standard plans, and the structural compliance of the system. And we're going to use the plan layout here of the house to illustrate a lot of these things, and then we'll go into the details of that. So here's our sheathing attached system. It looks like the diagram we had before because it is the diagram we had before. Again, we're not attaching to rafters, we're just attaching to sheathing, but we're staying more than 3 feet away from the ridge and the edges. That also makes sure that we don't have any problems with firefighter access pathways. So firefighter access pathways are not even an issue if we stay more than 3 feet away from the ridge and edges. Don't have to even go down that road. We said the 4 and 12 pitch. Let's see. This is a truss roof, and that's what we wanted to see. So it's a manufactured truss roof. And we're using 360 watt modules. There's 27 of them, 3 series strings of 9 modules in series on each, on the existing roof structure. And then we come off of the roof with this blue pipe, which comes down to the inverter. It's going to go down, straight down the side of the house, run along the edge of the house or down the eave and make it to our inverter, drop into the inverter, and then into the service entrance, which is service drop right on the corner of the house here. All right, so that's just a brief overview of what we got. Now we'll look at the electrical drawing. And this electrical drawing is a standard drawing where I just went in and I filled in the blanks. Okay, and so I've got a solar module, that's the AS360. 9 modules in series. That's for 3 different inputs into this inverter. It's got a rapid shutdown switch for compliance with rapid shutdown. All right, and it's got the American inverter, 7600 watt inverter. And then we're using PV wire, THWN-2 conductors for the conduit wire. So we got cables coming to the RSD switch, and then we have conduit wire with THWN-2 going from there. It's the type of wire. It's all 12 gauge wire coming up to the inverter. Once we get to the inverter, since we have a 40 amp circuit breaker over here, this is a 40 amp circuit breaker and a 200 amp panel. So the reason 7600 watts is the magic number is that's the largest inverter that you can run into a 40 amp circuit breaker. And that 40 amp circuit breaker is the largest circuit breaker you can put on a 200 amp panel and meet the requirements of Article 705 for the 120% option for how we would connect into a house. And that 120% option is by far the most common and simplest option in the code. It's just a matter of essentially installing a circuit breaker and mounting right to it. Any other method is going to be more difficult and more complicated, both physically and cost-wise. So that's the basic layout and the wiring. And so the wiring coming for that 40 amp circuit breaker is number 8 conductor, which is the standard side with the number 10 ground. All right, here's the notes pages, and this outlines the details of the module, the AS360 module. Here are the specs on that module, and then in the inverter, the specs on the inverter, the sign for the DC disconnect, the sign for the interactive point of connection, the distribution panel needs this sign, panel fed by multiple sources, utility and solar, and then the circuit breaker where we interconnect to the panel needs a warning, inverter output connection, do not relocate this overcurrent device, and then since it's got rapid shutdown, it needs to have the sign photovoltaic system equipped with rapid shutdown. All right. There's also information here about a visible brake switch, and so many, if not all, the utilities in Virginia require a visible brake switch. This is just like a knife blade switch you'd have, similar to what you'd have on an air conditioner, and that's got to be located typically near the meter is what they generally require. And so we have that in the plan. Let's just review that. That's this little disconnect over here. We might have a meter that the utility wants to see on the system, but it also may be a meter just for the owner as well, or for both. And we're in compliance, and we meet the 120% bus bar rule, so we're good to go. So that's the first example. All right, we're just about out of time. We're going to run through a quick microinverter example. Microinverters are where we put a little inverter on every single module. So in this case, we've got 26 modules instead of 27, and we've got 26 inverters instead of 1 inverter. So this is a little 295 watt inverter, and we're actually going to implement the 6-foot span because we're gonna be in an area of Virginia where we have low snow load, low wind load, and we're in exposure level B in a subdivision, and we met all those requirements. We could go to a 72-inch span possibly. We'd have to look at snow load requirements and stuff like that, so it may or may not. I'm just using it for this example. If it didn't meet the snow load requirements, if we had no place we could do it according to snow load requirements, then we'd go to 4-foot on center, and that would be the difference here. All right, so let's just take a look at this. In fact, this example, we probably use the 4-foot spacing. In fact, as I look at this, yeah, we went ahead and used the 4-foot spacing in the diagram anyway, and we even staggered. And so we're good all the way up to 60 pounds per square foot with this system. You can see that we're attached to every other rafter, and every other row is staggered. So it attaches to the different rafter. So every single rafter in this block here is attached to, and we can see from that system, it's different layout. We've got some south-facing panels, we've got some west-facing panels, but since they're all independent of one another, they're all running together into 2 separate circuits. So it says we've got 26 modules, we've got 26 inverters, and we've got 2 circuits of 15 microinverters each. Well, no, we're not going to have 15. We're going to have 13 microinverters each. So that's a checker trap there. Should say 13. Okay. So now we're looking at the diagram. We can see it's quite a bit different diagram than we have a standard diagram for the microinverters, and it tells us we have actually should be 13 and 13 in this, since we said we had 26. I'd have to go back and count all the modules on the roof, and so that would be part of my checking job. I got 4 here. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So 26 is the right number, and I'd have to go back here and say, oh, this guy's got to change to 13, and we're good to go. It has all the details about the equipment, the disconnecting means requirement. We have a little AC combiner panel where we combine the circuits together. That's very common for microinverter systems. And then it has manufactured cable to bring all that into a J box, a junction box here, where we transition the wire to a conduit wire, which is going to be that THWN-2 wire going into our AC combiner panel with 2 20-amp circuit breakers. And those 2 20-amp circuit breakers get combined together and go into one 40-amp circuit breaker into the 200-amp panel, just like the other project. Again, the largest residential system that you could put on a 200-amp panel following the 120% rule guidelines of Article 705. Here's the details, same module, different inverter. You can see that it's only, instead of 32 amp output, it's got a 1.23 amp output. And then we don't have a DC disconnect sign because it's a microinverter system. All we have is the AC PV system disconnect sign. And again, the panel fed by multiple sources, utility and solar, don't relocate the circuit breaker, and it does comply with the rapid shutdown. With that, I will land the plane exactly on time. You are on schedule. Keep your mask on as you depart the aircraft. And I'll turn it back over to you.
Yep, thank you very much, Bill. So thank you very much for that presentation, bringing us home with the electrical side of things. As I said, we have about 10 minutes left for questions. Feel free to send them in the chat, send them through the question feature. I did see one that came through. That was a bit earlier in the presentation when you were talking about grounding, I believe. And it was, should we require an additional ground rod?
Ah, excellent question. Well, thank you for that. And the answer emphatically is, it depends. So I'm sorry for that, but yeah, it really does depend. If the house has an existing grounding electrode system that is adequate, then my answer is no. And if the house has been built in the last, I would say 30 years, it probably has an adequate grounding electrode system. especially if it's a subdivision, because they're very standardized ground electrode systems and generally well built in the last 30 plus years, maybe 40 years. That being said, older homes might use water pipe grounds, and so a lot of jurisdictions around the country, if you have a water pipe ground, are going to require the driving of 2 ground rods 6 feet apart, because that's kind of a minimum requirement for ground electrode for smaller services. And so I would say that many jurisdictions around the country will say, if you're not a newer house, then we're going to require you to drive 2 ground rods. That's just for the grounding electrode system of the utility service. That is not for the solar. So the question may have been related to the fact that the way the code was written in previous code cycles before the 2017 code, there was an article, it was in Article 69.47D, it suggested that an additional array electrode might be required. The intent of that section was to say that if the building that you were installing, or the structure you were installing on, did not have an electrode system, let's say it's a detached barn that had no electricity in it, so it had no ground electrode system, that you would install a grounding electrode system like 2 ground rods on that barn, and then you tie the equipment grounding conductor from any disconnect equipment or distribution equipment to that grounding electrode system, and it has the benefit of local grounding as well as some lightning benefits and stuff like that. However, if you were to install it on a typical residential subdivision house that was built in the 1990s, that house already has an adequate grounding electrode system, and no additional array electrode was ever intended to be required, even though many jurisdictions have tried to, or thought that it did, because it wasn't well written. Quite frankly, I put in the original proposal for that additional array electrode back in 2008. The code panel at that time, which was not me, kind of all screwed it up, turned it into a lightning protection requirement. And then when I got on the code panel, shortly after that, been trying to get it revised to say the right things. And the 2017 code, which Virginia is on now, does have it correct. And so that basically just says that if the structure doesn't already have an electrode, then install one. If it does, don't worry about it, because your equipment grounding conductor connections are already going to give you everything you need, and you can't improve that. One last note about that issue, because it's a big issue. It's actually caused a lot of consternation for both installers and jurisdictions around the country. Some folks say, well, you know, it doesn't hurt anything to drive an extra ground rod, and I take issue with that particular question. We actually had a fatality recently, about a year ago, here in California, where a gentleman drove a ground rod, and because they thought the jurisdiction was going to require them to have it. It was an additional array electrode, and they hit a gas line. And that person did not die, fortunately. They stopped. They realized they hit gas. They smelled it. They stopped what they were doing. They realized that if they hit it again, they could cause a spark and be a real big problem. And so they stopped what they're doing. They called the gas company. The gas company came out. There were guys still working up on the roof. There was a lady who was in the house with her baby. She took her baby out to, I think, a relative or something in a car. She went back to get a diaper bag, turned the light on. The house exploded. The folks on the roof were blown off the roof. Both of them survived. The woman walked out of the house miraculously, but the gas person had already shown up and was starting to work on trying to figure out what was going on with the gas. The gas person was killed instantly. And so Yeah, I mean, every part of construction has dangers to it, and so we don't want to add construction requirements for things that are not required. That's kind of a broader issue, but that's an example of somebody who was killed because of that. So anyway, any other questions about electrical? That was actually an excellent question.
Yeah, thanks for that answer, Bill. And actually, it was brought to my attention that Virginia is actually still under the 2014 NEC.
Yeah, so whenever I have questions about what code cycle, I always go to my NEMA Adoption Map, NEC Adoption Map, and that always helps me because I mess this up all the time. And so we pull up the adoption map, and they keep this thing current. And there it is, the 2014 code, and that's as of August 2020. And thanks for that. I appreciate that. And so that also, because of the language in the 2014 code, does confuse some folks about whether or not that additional array electrode is actually required for houses that already have an electrode. And for those of you who are really into it, and obviously the person that asked it probably is really into it, there are two exceptions, and one of those exceptions has to do with if it's serving loads where there's already an electrode available and stuff like that. And so those exceptions were intended to relinquish the requirement for, or provide an exception for a requirement for houses that already had electrodes, because every house has an electrode. And then it's just the question of whether or not the house has an adequate electrode. And that's always a question. When anyone's doing an electrical project, it is an opportunity for the jurisdiction to review the grounding electrode system of the house. And if that grounding electrode system is inadequate, which over the years in older houses, in many cases, the answer is yes, it is inadequate, then it needs to be improved. But it's not just because it's solar, it's because that's a basic requirement. And so as long as you get that grounding electrode system up and going correctly, then our attachments of the grounding electrode to it are safe, are good, and there's no need for any more than a good grounding electrode system, if that makes any sense. And that would be consistent with the 2014 code. Anyone know when the 2017 code is due to be adopted in Virginia? I'm sure COVID has screwed everything up on that schedule as well, but.
If anybody knows that one, throw it in the chat.
Yeah. So, go ahead.
Oh, do you have another question that just came through, Bill? Is a solar panel a sub-feed with separate, or with ground and neutral are separate?
Well, that's an interesting question. So that would assume we're talking about an AC output. So these AC outputs, the grounding and the neutral are always separate unless you're talking about a service. A service, the ground and the neutral are derived together, and that's what we call a derived system. And so the ground and the neutral are attached at the service, and then anywhere we make a connection other than the service, the ground and the neutral are always kept separate. And in this case, we're going to go into a circuit breaker. If that circuit breaker is in the main panel, then the circuit breaker is going to go snap into the bus of the main panel. The neutral is going to go to the neutral bus bar. The ground is going to go to the ground bus bar. But in that main panel, they're tied together. So they're actually going to be bused together in that panel. However, if we were to make that exact same connection to a sub panel, which would be, let's say, a 100 amp sub panel inside the house somewhere, and the main service disconnect is, say, let's say on the outside of the house, as in our examples, then that sub panel, the neutral and the ground, will be separate, as all the circuit breakers in there are. And so we install the circuit breaker for these interconnection breakers exactly the same way we do any load breakers. There's no differences whatsoever. And the panel itself would decide whether or not where you are in the world as far as whether the neutral and the ground are together. But they're going to be physically separate wires. And some inverters don't even require neutral at all. So that's also something to be aware of, is that you'll see these inverters are putting out 240 volts. There's no 120 volt loads or anything going on the neutral. And so they may only be a line 1, line 2, 2 hots, and a ground wire. And in that case, it's super simple. The ground just goes to the ground, hots go to the breaker, everybody's happy.
Great. By the way, we did get an answer on the adoption of 2017. It's been suggested that that will be next year.
Right. Good. Yeah, well, I'm sure it got delayed because of COVID as well. The 2017 code has a lot more information, is a more pared down version of Article 690 for PV systems. Article 705 is very, very similar. So the interconnection part, the part we just talked about with circuit breakers and all that, how it interconnects to the building, that's all virtually identical between the 2014 and the 2017, because the 2014 code, I was very involved in the rewriting of those requirements, and that was probably the biggest benefit of the 2014 code, was getting those interconnection requirements really well nailed down. And then the 2017 code, we did a lot of cleaning up of Article 690 to make it easier to read. But the stuff that we covered last time and this time, especially with the electrical, is all relevant, and the 2014 code is a wonderful code for that, and we didn't give you any information that would be in conflict with your current code. And the next time we're going to be talking about inspections, field inspections. So many of you on this call are probably field inspectors. We're out of time. Thanks for participating and thanks for showing up. And I'm glad that I was able to make it back in time to meet with you all.
Yep, exactly. And I'm just going to share my screen real quick as a reminder. Next Tuesday, August 25th, from 1 to 2 p.m. Eastern Time, will be the session on field inspections. I'm sure we'll have some time at that point to also take some Q&A. We can take those live through the chat or the question feature. If you do have questions in advance, feel free to send them over to me as well, kaza@nlc.org. And we will also send a follow-up email with the recording from today's virtual training as well. So with that, Bill, once again, thank you very much for being here today with us. Hope your family stays safe and healthy out in California, and the cleanup and rebuilding can begin quite quickly. Thank you very much to everybody that attended today, and we do hope to see you on Tuesday for the final session in this 3-part series. So thank you all very much, and have a good day.
Have a great afternoon, folks. Thanks for participating. Take care.